last Friday. So I have put some stuff up on Moodle. I've put this file here. Yeah, just this PDF which shows you some guidance on the exam. Just some thoughts on how to prepare for the exam. So, in principle, you should revise everything, and don't just look at the past papers. Do look at all the stuff and make sure you know everything. So, first of all, definitions. So the key, basically all the definitions in the course, you're expected to be able to know the definitions and to be able to give precise definitions of the concepts that we meet in the course. And you'll see in various of the past questions, you'll see those kind of questions come up saying, give the definition of this, give the definition of that, okay? And that's your opportunity, to show your good, clear understanding of the material. When you're giving definitions, it's often good to give examples as well, both positive and negative examples. Things that have that property, whatever it is, things that don't, or as appropriate. So there's lots of different kinds of exercises in the notes. Some questions in the notes are more straightforward than others. You'll have found and realized some are longer than others. This list here, what I've done here is I've gone through all of the exercises in the notes and I've indicated the ones, that could reasonably make an appearance on the exam. Those are good exam questions to kind of look at as well. The ones that have been left out of that list are the longer, more investigative exercises, okay? Maybe some of the more challenging exercises that led us to further results in their own right, okay? So those, as well as the past exam questions, that list there from the tutorial exercises will give you other indications as well. Sometimes you're asked to give proofs, and as appropriate, there's often some guidance worked into the phrasing of the question, some guidance or hints or direction worked into the question. Do take account of those, and do follow the instructions. I'm normally putting those there, for a point to help you and to guide you on that. Yeah, give as complete a presentation as you can. You can use the part marks on the questions for guidance for timekeeping. So I'm sure you're well practiced at. I like to use the rule of thumb. It's so you have to do 5 questions. They're all worth 20 marks. So I suggest setting aside half an hour for each question. And then those 5 half hours, 2.5 hours, that still leaves you with an extra half an hour then for tidying up, spending longer on certain bits, going back and checking things and so on. And you do make use of other results to construct your proofs, as long as you clearly indicate where you're doing that and demonstrate your understanding that you're basing this proof on results of prior concepts as well. Now, so due to constraints in the exam, to do with the length of time you have and the reasonableness, you won't be asked to produce some of them longer, more difficult proofs. So what I've done here is I've looked at chapters 2 and 3, and I've picked out, again, the ones that would be reasonable to ask for proofs of in the exam, okay? Just to give you some guidance on what results I think are reasonable to ask in an exam and which ones aren't, okay? Then the last type of questions, so these do come up, I do ask these from time to time, you'll see them on past exam papers, is descriptive type questions. So it's not a prove this question, it's not a calculate this question, it's not give this definition. It's a more looser kind of descriptive kind of little mini, I wouldn't say essay is stretching it a bit too much, but a discursive treatment of a topic, okay? So for instance, you might get, these are questions that I've either asked on previous examples or on previous exams, or I think would be reasonable questions. Give a description of how the Euclidean algorithm works. Demonstrate your understanding of the Euclidean algorithm. You want to clearly say, What job does it do? What job or jobs does it do? What inputs does it take? What outputs does it produce? How does it work? Why is it that the GCD, or the number it spits out at the end, why is that the greatest common divisor? Kind of ask that kind of question on the coursework. It's an algorithm. So what aspect of it is it that guarantees that it does stop after a finite number of steps? So there's something you give to the computer to do. Other questions: how should one approach finding the solutions of a general polynomial congruence, f of x congruent to 0 mod p? So you'd be talking about, the various intermediate results that led up to that. The Chinese, this is fx equal to 0 mod p. Also equally well, I could ask you mod n as well. If it was mod n, then you'd want to start talking about the Chinese remainder theorem. How you factorize n and base the treatment on that. Or another option would be, what techniques are used to evaluate the Legendre symbol, PQ? The two very large primes being Q. Okay. So that's what that's referring to as the factorize, flip, reduce procedure. Remember that factorize, flip, reduce algorithm we did recently for evaluating Legendre symbols? So you'd want to give a descriptive treatment of that. Okay? Describe those three processes, what results justify them, and why is, you talk about why is it an algorithm, it's there's no arbitrary choice involved, just very clear what to do at each step, and it's why does it stop after time, because the arguments are getting smaller all the time. So okay, so that's a bit of a guidance document which is on Moodle on the past exam, the number theory side of the exam. There's various material put up there. So on the library block on the right hand side, you've got the last 2 years exam papers. Over here in the middle, this section near the top, just under our photos, I've got the 2015 exam as well. And there are also these solutions, the worked solutions, in those PDFs to the 2016 and the 2015 exam. And there's a set of video solutions, which I made last year, of me talking to the solutions to the 2014 exam. Okay, and the 2014 exam is given there as well. Yeah.
Just check, it's not a completely question, is there? It's just that we have to choose the order.
Yeah. So I've got last year's paper here now. So that'd be a good time to look at this. Yeah. So the structure is there's 4 number theory questions and 4 cryptography questions, and you have to do 5 questions in total, which must be 2 from number theory, 2 from cryptography, then your 5th question. So it more or less forces you to cover about halves equally. Any other questions just before we get into it? Okay. So start having a look at this, and we'll use it as an opportunity to revise as you go. And if any questions come up, do ask as we go along. Okay, the print off. Yeah, I forgot to use the double-sided. Okay. So yeah. Okay, so this is the last year's paper. So there's, as I said, there's 4 number theory questions for cryptography. The 4 number theory questions is, question 1 is roughly on early stuff, the definition of divisibility, greatest common divisor, Euclidean algorithm, induction. Second question focuses on prime numbers. Some of the nice results concerning those. Question 3 is about congruence and polynomial congruences. And question 4, kind of all about quadratic residues. Okay. And then there's the 4 cryptography questions as well. So let's go to question 1, and I'll kind of go through how I would answer these questions. But please do interrupt any stage, ask any questions you have, or if there's any related questions to concepts related to this. And that question there pretty much covers what's in chapter 2. So in chapter 1, in chapter 1 we were introducing the integers, and the main thing there we were focusing on was the principle of induction, the proofs by induction, and kind of how induction is the kind of quintessential property of the integers. There's an induction proof question there in question 1 part D. In chapter 2, then, we introduced divisibility, gave the definition, gave all its properties, one of which is asked in question 1A, but we have this kind of early theorem 2.1. Property 3, the divisibility of linear combinations, came up again and again and again and again. We were constantly referring to that throughout the course. We did a quick look at prime numbers. Of course, you can, once you got divisibility, you can define prime numbers. Then we looked at common divisors, greatest common divisor. That brought us to the Euclidean algorithm as well, and Bezout's identity. So working the Euclidean algorithm both forwards and backwards to get the GCD and to get the linear combination and so on. Okay. Then we had a few results on properties of the GCD and the associated concept of the least common multiple. Greatest common divisor, least common multiple, kind of mirror images of each other. And then you have a whole bunch of questions here which tackle all of these things. Okay. So let's have a look at question 1. The question 1A says, write down, 2017, question 1A, write down the definition of the divisibility relation, A divides B, and use it to prove that the relation is transitive. If I was being slightly harder, I'd just leave it like that. Don't remind you what transitive is, just expect you to know that. I would expect you to know what we're talking about when we say transitive, but transitive is the property of a relation that says if the first is related to the second related to the third, that implies always that the first is related to them. The relation travels through the intermediate curve. Okay? So in this context, here it means that if an integer A divides B and an integer B divides C, then we can conclude that A divides C. So first we want the definition of the divisibility relation. So we just want a clear version of that. So you could say, we say A divides B, and write it as A divides B. I read it. So how do we say that? Well, of course, the idea is A divides into B in an integer sense. Okay? B is a multiple of A. So we can say if there exists another integer C such that B is equal to C times A. I would give a couple of examples. Say 3 divides 15 as 15 is equal to 5 times 3. Simple. For completeness, just to hit everything, I'd give a negative example as well. 2 does not divide 15 as 15 equal to 2 by C has no integer solution C. Yeah. That's pretty much everything in the definition of indivisibility. Okay. Of course, the one thing just to, if you tend to get things mixed up sometimes, your left and your right, your up and your down or whatever, Sometimes people see this and they think it's, oh, A can be divided by B. A is the big thing and B is the small thing. No, that's the wrong way around. So, and it is maybe confusing because we think that it's similar to, I hesitate to write it there, but to writing fractions like A over B, then kind of maybe A is the big thing and B is the small thing you're dividing into. But it's not that, it's the straight line divisibility sum. So it's read as A divides B. So A is probably the smaller integer, B is the bigger one. And B is getting divided by A. So if you're prone to making those kind of errors, come up with a way of fixing it in your mind and making sure you don't. Okay, so we have to prove it's transitive. And here's the proof of transitivity. Now in your proofs, we want to, give enough detail. I would say proofs are in English with a bit of mathematical notation provided. Don't try and not have no words in your proof because maths is English after all. So when you're writing it down, also the important parts of proofs are what's going into the proof, what are the assumptions that you have, what's the information you already know about the objects you're talking about, and what the conclusion you're trying to get. So you really want to make those very, very clear. Don't have some kind of wandering argument that mixes up assumptions and conclusions and kind of makes, doesn't convince the reader that you have a clear understanding of where you're starting and where you're going to. So I would have a nice introduction of saying what the objects are, even though they're kind of stated what they are in the question, but to give a coherent answer, let's declare them again. So we'll let integers A, B, and C be in Z, and suppose that so what was it? A divides B and B divides C. And don't panic in the exam if you start, if you don't immediately see how to do it in your mind. Think of the steps we go through to kind of construct these proofs and to find our way through these arguments. First of all, make it very clear what the starting point is. So you clear up their information that you're giving yourself. And then down at the bottom, then you have the conclusion. So the conclusion we're trying to get is A divides C. Whether you sketch this out on a rough worksheet or just sketch it out in your mind, this is your task, to go from here to here. And that can be done by pushing forward your assumptions or drawing back your conclusions. What do we have to achieve in order to declare that A divides C? Well, you see, it's sitting up here in your definition. A divides C, we will say, when we can write B as something times C. Okay. So that means previous to making this declaration, I must have been able to write C as something times A. So there's a gap here at the front, okay? And into here it must go an integer, okay? Because there has to exist, so, okay, this is called C up here, but there has to exist some other integer that you can write the first one as a multiple of the second. I want to say A divides C, or sorry, but the second one is multiple of the first one. So I want to find this other integer that says that C is equal to that integer times A. And it's going to come from up here, of course, from your assumptions. So see there, I roll the conclusion back using the definition. Well, you want to do, you do the same similar thing to your assumptions. You roll them forward using definitions. That's one way to roll them forward. What does it mean to say A divides B? It means that we can write B as some A times alpha, and we can write C as some B times beta, and that can be done for some integers, alpha and beta. Or you could say it, i.e. there exists integers alpha and beta such that B is alpha A and C is beta. So, I mean, I left way too much of a gap there because really then it's just a substitution. Yeah. So, I mean, that implies that we can write C, B beta, but then we replace the B by A alpha beta. And I mean, getting this conclusion here is literally just introducing parentheses just to emphasize the structure here. We don't normally require parentheses because multiplication is associative of numbers. We need to know as well. I mean, that's probably over-egging it and kind of saying the same thing twice there. But that pretty much is your proof. You know, maybe just add in from the definition of divisibility, and here we roll that forward. That was by the definition of divisibility. To make it clear, it really just requires a couple of uses of the definition of divisibility and a bit of, you know, fairly straightforward substitution. And I mean, what do you substitute into what? Well, you see, once you know that your destination is an equation with C on the left, then you ought to focus on this one first because that has C on the left. This one has an A in it, and you require the right-hand side to have an A in it, so, you know, some kind of squishing this into that. Okay. So that was 6 marks. Okay, any questions? So, like, I would expect you to be able to tackle in a similar way any of those parts of theorem 2.1. Any of those parts of theorem 2.1 would be reasonable questions to ask. And find your way through the proofs of them, you know, using similar approach and principles that we saw there. Okay. Question B is, again, another definition one. Write down the definition of the GCD of A and B and explain how the value of GCD AB is characterized in terms of linear combinations of the two integers A and B. Okay, so first our definition. So we'll spell out what it is. It stands for the greatest common divisor. Greatest common divisor, written GCD AB. And, well, what are these A and B? Those are any two integers A and B, is basically the largest integer, let's call it D, such that D divides A and B divides B. And I didn't qualify A and B's. Maybe some books will say not both 0. I mean, there is a little bit of ambiguity about what you do when A and B are 0. I mean, what's the greatest common divisor? Because you see, we say that everything divides 0. Yeah, because 0 can be written as a multiple of anything. So, well, that tells you there's no greatest. But there is kind of a reasonable way to say that the greatest common divisor of 0 is equal to 0. You could say that by definition for consistency. That would make this case of 0, 0. It would keep it being it would match everything in the transitivity of divisibility and so on. And there's a sense in which, you see, really 0 does sit at the top of the hierarchy of divisibility. Everything divides 0. So we normally think of 0 as being small, but in the divisibility sense, it's kind of big. It's everything is a factor of 0. In a trivial kind of way. I wouldn't deduct any marks or anything if you haven't addressed that. Okay, so that's, I mean, is that a clear definition? The greatest common divisor in two integers is the largest integer d such that d divides a and d. Pretty straightforward. Maybe give an interesting example, e.g., so I think of 20, 24 and 10. Interesting. 24 and 2 and 3, something else with it. 24 and 30, let's say. GCD of 24 and 30. Six. Biggest integer that divides it. Okay, so that second part was how is it characterized in terms of linear combinations? So then we just need a very clear, precise statement. Now this is the statement of theorem. Now, of course, you don't have to know the numbers of the theorems. This is theorem 2.3. I'm just putting this here for cross-reference. I mean, you're not expected to remember these numbers in the exam by any means. So a theorem declares that D, which is the GCD of A and B, is the smallest positive. So there's two things we want to be very clear here. The smallest positive, strictly bigger than 0, smallest positive linear combination of A and B. Linear combination of A and B with integer coefficients, just to really pin it down. Okay. So D, in other words, D is the minimum of the set of all linear combinations of A and B, such that alpha and beta are integers, and alpha A plus beta B is strictly bigger than 0. I've given it in an English definition, and I've also written it out symbolically as well. I mean, I would be happy enough with just that precise sentence first, but you can give a normal symbolic definition of it as well. So it's the minimum of this set. Okay? This is a set of positive integers, so it does have a minimum. Set is infinite, of course. There's infinitely many linear combinations you could make, but it's an infinite set of integers that's strictly bigger than 0, so there will be a smallest. Anybody remember what that property was called? Again, this wouldn't be required to be part of the answer, but just a little note. This minimum exists because of integers are. See, this, if you were just talking about linear combinations that had rational coefficients, or real coefficients, alpha and beta, of course you couldn't talk about the minimum of such a set. Because you could arrange arbitrarily small values of this linear combination just by tweaking your alpha and beta, if they were allowed to come from the set of rational numbers or real numbers. But because alpha and beta come from the domain of integers, fundamental kind of axiomatic property of the integers, remember this, it's related to induction. Boom, yes, well ordered. Well ordered. Excellent. Okay. That's a property that basically says every non-empty subset of the positive integers has a least element. It seems obvious when you think about it, well, of course it is. But it's this kind of axiomatic property that the integers have. It's equivalent to the principle of induction. You can't do induction over the rationals. You can't prove a statement about a base case rational and prove that if it's true for one rational, it must be true for that rational plus 1, or even plus something tiny. Because every time you do plus 1 from a rational, of course, you skip over infinitely many rationals. You can't prove everything about all rationals by some kind of inductive argument like that. And the rationals are not well ordered. Yeah. So good. that all for question B? Yeah, 4 marks. Okay, any queries? Or... C. Okay, use the Euclidean algorithm to calculate GCD of 1, 2, 6, and 36. Give brief explanations for the main steps of the algorithm and explain why the output produced is the GCD. This is more or less the coursework question, isn't it? The first coursework question. Okay, so what would we do here? So, well, we want to say there's a sequence of integer divisions. So you're dividing, how many times that goes in 4 times probably? 420 and no, 3 times. 3 times is 90, 108, remainder 24. 28? 28. Yeah, of course it is. 26. Yeah. Then, okay, that's well and good. Then what do we do? Then we take the 36 and we attempt to divide it by that remainder. So the 36 is 1 times 28 plus 8. Then you take your 28 and attempt to divide it by 8. 3 times 8, 24 plus 4. And you take your Then you take your 8 and you attempt to divide it by 4, which you can do. 8 is 2 times 4 plus remainder 0. So let's say the last non-zero remainder is the GCD. One, 3, 6, and 36, i.e. 4. Okay, that's the operation of the Euclidean algorithm, but you see, the question is asking more. It says, give a brief explanation for the main steps of the algorithm. Okay, there's our sequence of integer divisions, and why the output produced is the GCD. So, in each integer division, A equals QB plus R, we have, well, say something about the remainder. The remainder is always strictly smaller than the absolute value of B. B might have been negative at the beginning. It can handle negative numbers. But the point is, this remainder is i.e. smaller than B. And second point about this is the GCD is preserved in the sense that the GCD of A and B is the GCD of B and R. Okay, we're stating these results. We're not going and proving them necessarily. Didn't ask for like a full ground up proof, except explain why the number produced is the GCD. So in each integer division, A is smaller than B, and the GCD is preserved in the sense that GCD of A, B, GCD of B and R. So at the end we have GCD of 8 and 4 equals GCD of 4 and 0, which by definition is 4, because everything divides 0. I mean, you could put these, I think at the notes I put these GCD statements, so I kind of paired them all with the thing up here. So that says the GCD of 1 through 6 and 36 is the GCD of 36 and 28. This would say the GCD of 36 and 28 is the GCD of 28 and 8. And this would be the GCD of 28 and 8 is the GCD of 8 and 4. So this last one would say that, well, this is this last one down here. The GCD of 8 and 4 is the GCD of 4 and 0. So just kind of asking you for a nice example of the Euclidean algorithm and just to kind of say some important things about it, explaining how it's working and why the output produced is the GC. And note that the sequence of integer divisions is finite. You didn't really ask about this algorithmic point. I think you would have gotten full marks up to here. But I think it's good to point out the fact about the decreasing remainders and the fact that they must terminate because they'll eventually hit 0. So the sequence of integer divisions is finite as the remainders are decreasing and greater than or equal to 0. Again, this is this well-ordered property, I think. A sequence of strictly decreasing integers, but if they're all positive, or if they're all non-negative, then they must eventually crash into 0. So that's a pretty much I'm trying to hit all the buttons there, so to avoid losing any marks. Good explanation. Good. Remember the exam. You're trying to demonstrate your understanding. Okay. Don't be afraid to put in to show off basically, and to do your best to address it. Yeah. Okay. And finally, this question is proof by induction of a divisibility formula or divisibility result. This will be part D. So we're proving by induction that 8 always divides. Claim is for all n bigger than or equal to 1, 8 divides. Okay. It's true for n equals 0 as well, but 8 divides 3 to the 2n plus 7. Okay. Yeah, you could criticize me. You could say actually it works n equals 0. So in a proof by induction, so we could say the proof by induction begins with the base case, n equals 1. So examine this thing for n equals 1. So it's 9 plus 7, so it's 16, which is clearly divisible by 8. Okay. So 8 does divide 3 by 2 times 1 plus 7. So the base case is true. Remember, proofs by induction, like this, these ones, they always begin with the base case, okay, which normally is just a simple observation, straightforward observation, or checking. Then we make an induction assumption, okay? So we assume claim is true for n equals k. K is some number bigger than or equal to 1. And that is a reasonable thing to say because we know it's true for 1. So it's not a obviously self-contradictory thing to say, well, let's pretend it's true for some k bigger than or equal to 1, because it is possible to do that. You might worry about arming yourself with that assumption if it was possible that it was never true for any k bigger than or equal to 1. Anything you work off that assumption is not relevant to the real world, because if it's never true for any of these k. Well, it is true for some k. And I would say, I would spell out that assumption. So i.e. what that means is 8 divides 3 to the power 2k plus 7. And now what we're trying to do is we're trying to conclude that it's true So the claim is true for the next value, n equals k plus 1. Okay, that's the structure of the induction proof. And you know that you should know that ahead of time. But that's basically the structure you're trying to fill out. Okay, well, so now you start squeezing it. Okay, what does it mean the claim is true for n equals k plus 1? It means you want to reach the conclusion that 8 divides 3 to the 2k plus 1 plus 7. That's what it means for the claim to be true for n equals k plus 1. Okay, now you got these two statements about divisibility. This whole question has been about divisibility. Very first part was getting you to give the definition of divisibility. Okay. So it seems that either we're going to base this on operating on the divisibility level using properties of divisibility, or maybe we can roll these statements back to their statements just about products of integers, and then just use more basic kind of algebraic manipulation type arguments to get there. Okay. So I would do that. I mean, what does it mean to say 8 divides this? It means we can write 3 by 2 to the k plus 1 plus 7 as something times an 8. Okay, and this something has to be an integer. And see, once you realize this here, that this is what you're trying to get to, then that tells you how you should work from up here. Okay. From up here, you should start with this quantity here, 3 times 2 to the k plus 1 plus 7. And we're going to work on it and work on it and work on it and try and squeeze an 8 out of it. Okay. And leave behind an integer. But we have to use our assumption, or if you're wandering around in an argument here without using your assumption, you're probably not going to get very far. Okay? What we're trying to do at this stage is prove the inductive link, inductive step. So if you're not allowing yourself to make use of the assumption, you're probably not going to get there. Oh yeah, I didn't roll forward the assumption. So the assumption says that 3 to the 2 times k plus 7 is equal to 8 times alpha for some integer alpha. Okay. And even just literally naming that integer on the page helps you in the argument, because it gives you a way to talk about that integer and you can introduce it in your argument further down. Now this, you see, now it's clear. The thing you're trying to prove it pretty much almost looks like the thing you're assuming. Okay, you got a power of 3 plus 7 equals 8 times something. That's exactly what we're trying to get to. A power of 3 plus 7 equals 8 times something. Now the powers are slightly different, not a huge amount different, slightly different. So the general way I present these is, well, take this thing here and maybe draw out this factor here, the 3 to the 2k plus 7. It's nearly there completely. So this is 3 to the 2k plus 2 plus 7. And that can be written as 9 times 3 to the 2k. Got 9 by 3 to the 2k. You still got your plus 7. At this stage, this is where the little, I don't know, kind of trick or manipulation is needed. Maybe it depends on how you set up your equations, but you nearly have it there. It's 3 to the 2k plus 7, except it's not quite, just because the 3 to the 2k is multiplied by 9 first before you add 7. So you just kind of, you say, well, no, I want to add the 7 first and then multiply by 9. And that'll give it to you, except doing it this way gives you 63, but we only want 7. So we want to take away something from 63 to make it 7. So what was that? 56. Okay, minus 56. It's like completing the square or type. You force it into the form you want, and that introduces a necessary correction. But of course, the correction, of course, is divisible by 8. You see. So this means now I can write it as not. You see, this 3 to the 2k plus 7 is 8 alpha. So there's my alpha. I got to also multiply it by 9. So I'll have 8 times 9 alpha. So that will give me 9 times 8 alpha. It'll give me this part, but minus 56, so it's minus 7. And it's all of that. Yeah. Okay, so this was like algebraic manipulation. Here we're from assumption, we can just say. For bringing in our alpha. So that's pretty much it. We got base case, assumption, pushing the assumption forward to the truth of the next case. So claim is true. Claim is true for all n by the principle of induction. That's just the kind of final declaration that you're claiming is true next. You proved all the necessary steps and proved by induction method. So that was question 1. Keep going with some of the other questions in our classes and tutorials. But you should be looking through it, and any particular questions or queries you want to bring to the lectures or the tutorials, do bring them along. I'll address them all as best I can. Okay, finish there for this morning.